How you doing? I'm Mr. Rose, and today we're going to work a problem that is really an understanding question that you can see right in front of you here. We're really going to try and get an understanding of what this drift velocity is. Now, we are talking about current and electricity traveling through wires. And we've spoken about this before, but contrary to what a lot of people think, electrons are not flying through super fast, one at a time in a linear fashion through wires. Electrons or charge carriers, we want to say, will really kind of go in some random order, some random fashion. So instead of talking about one electron or one charge carrier after another as a current, this drift velocity, the charge carriers flow through that wire. So we are going to try and make a relationship, excuse me, between drift velocity and current such that we can really understand what's happening in this wire. So this is a real, actual physical thing. So again, take a look at this question. You see I highlighted in red some of the important things we're going to really dive into understanding. And let's get right to it. All right, so now I'm hiding off camera, but you can see we have the question here just like you saw. It's not going to be the best production, but this is, kind of the best I can do during our COVID kitchen. Yes, this is my kitchen. So physics in the kitchen. Excuse me. So where are we going to jump right in? Things that we need to know. Again, we know that our wire is a real thing, right? So this radius of my wire, that means the wire has some actual thickness. That's going to be important to us. Then this red is some stuff that we highlighted that we really needed to know to understand. Some things that you could look up in a book, some nice and easy, is the molar mass of copper. You'll understand why we need that momentarily. But the molar mass of copper is 63.54 times 10 to the negative third. We also need the density of copper, which I have here. And just for simplicity, we're going to assume that we have a uniform J and or drift velocity. In other words, there's one conduction electron per atom. So now what are the things that we know? We know we're looking for this drift velocity, so let's remember that drift velocity J is equal to the number of charge carriers times the charge of my electron, or my charge carrier is E, times the drift velocity, Vd. We also know that the drift velocity comes from an application of Newton's second law. We know that the electrons, or the charges, are drifting down, hoping this is big enough, are drifting down the wire due to some electric field because we applied a potential difference divided by the mass of every charge carrier times that tau, which we learned is kind of like an average time, but tau is the time between collisions. Then we also know we can relate current, J, the drift velocity rather, to current per area, right? So we're going to really tie all these things in. Now, even though I wrote this, this would be super useful if I knew the electric field. I don't know what the electric field is, so that's not really helpful. I don't know what tau is, that's not really helpful. I mean, these two things I know, but this is going to run us into a dead end. So what are the things that we know? Well, that we can figure out. So I did say that this molar mass eventually would be important. Well, why would that be important? We can figure out actually how many atoms of copper there are, right? Based on my assumption, if I know how many atoms of copper, maybe that'll help. Why or how do I do that? Perhaps you remember from chemistry Avogadro's number, which I tend to need to look up. But Avogadro's number, 6.02 times 10 to the negative 23rd. So what we're going to try and do is we're going to try and figure out n. We need to know this n. How many, how many atoms of copper we have. So to do that, I'm going to say n is equal to, we have a molar mass, so I want to know how many atoms per mole. Okay, what am I going to do with that? If I know how many atoms per mole, and then I know how many moles per unit mass, right? If I know how many moles per unit mass, do you see where I'm going with this yet? And then I know a mass per unit volume. mass per unit volume, I can multiply all that together, and what am I left with? I am left with a number of atoms, the number of atoms per unit volume. Well, sorry, you couldn't see anything I wrote down. So that's everything that I wrote down there. So since copper has a molar mass that we can look up, that's given, and the density is constant, we know what that is. These are known things that you can look up. I didn't just have to give them to you, but we can find them. If we know all that, you should be able to figure out that number n. So this is going to point us in a direction. Again, all things we can look up. I wouldn't expect you to just bring this stuff right off the top of your head, but I'm hoping it makes sense on why I'm going this way. So let's see. If I remember Avogadro's number, I told you I don't remember it. I tend to look it up. Avogadro's number, I think, is a capital N, 6.02 times 10 to the 23rd, and that's a mole to the -1. So to get my n, my little n, my number of charge carriers here, I'm going to say n is equal to Avogadro's number. I'm just going to define n naught, times, I want my molar mass, right? So this is going to be times 1 over the molar mass of copper, 63.54. 63.54 times 10 to the -3rd, and that is kilograms per mole. And then I'm going to multiply that by the density, that mass per unit volume, by my density, which is given here, 8.96. 8.96 times 10 to the 3rd kilograms per meter cubed. And if I do all of that right, we should get 8.489. I'm going to take an extra decimal. 89 times 10 to the 28th. And that is going to be our number of electrons per meter cubed. So we're going to have, that is going to be an electron per meter cubed. Now, what am I going to do with that exactly? Trying to get more paper here. Oop. There you go. What are we doing with that exactly? Well, now that I have my n, I can just go, I'm going to plug straight in to J and E times VD, right? So I'm going to say J, my drift velocity, is now, I know that I have this 8.49 times 10 to the 28th electrons per meter cubed. Beautiful. I know the charge of an electron. I know that is 1.6 times 10 to the -19th coulombs, but I still don't know this drift velocity yet. So this is going to be a little bit of a hang-up, but again, I also know that I want to recall J is equal to I over A. All right, well, why is this going to be helpful? Well, I know what A is. I'm going to set these guys equal to each other. I have I over A equals 8.49 times 10 to the 28th times 1.6 times 10 to the -19th times my drift velocity, which is eventually what I'm trying to figure out, right? I believe earlier I called J drift velocity as opposed to current density. If I did that, I'm not going back and re-recording this, so J is definitely not drift velocity. J is definitely our current density. Whew, sorry. But anyhow, now that I know my current density, and I hopefully corrected that issue, A, what is A? A is the area or the cross-sectional area of my wire. Wires have a cross-section that looks like a circle, right? So I know A is just apple pi raised to 2 pi r squared. Pi r squared. So now I have this I over pi r squared equals, I'm just not going to write that out. I'm going to go back to my equation just because it's easier, equals n times e times that drift velocity, which is what we're still trying to find. So now I can rearrange, and now I can say that my drift velocity on camera, my drift velocity is equal to, I have an I over pi r squared times n times e, the charge of my electron. Yeah, that looks right. So last thing I have, this is my general solution. Go back to my given, and hey, I had a uniform current, 17 milliamps, if you recall. Now it should be easy, just plug and chug. And if you do all that right in the calculator, you should get 4.92 times 10 to the negative 7th meters per second. So what does that show us? That shows us with real values that electrons or charge carriers actually travel very slow through wires. That is all we have for you, going over our hopefully super in-depth understanding question. If you're watching this on my YouTube channel, by all means, feel free to like, comment, and subscribe. Keep questions coming, and you will hear and see from me next time. Hear from me and see me next time.